Imagine you have a book. You toss it into a fire. The book burns, turns to ashes. Smoke rises into the atmosphere. Now here's a question. Is the information in that book truly gone? According to the fundamental laws of physics, the answer is no. If you were some sort of cosmic detective with perfect knowledge of every particle's position and momentum, you could theoretically reverse the burning process and reconstruct not just the book, but every single word on every page. This principle, that information is never truly destroyed, is one of the most sacred rules in physics. But in 1974, a young physicist at Cambridge University discovered something that would seem to break this rule completely. His name was Stephen Hawking, and what he found would spark a debate that continues to this day: the black hole information paradox. To understand why this paradox matters, we need to talk about what physicists mean by information. They're not talking about knowledge in the everyday sense. They're talking about the complete quantum state of a system. Think of it like this. You have a cup of coffee sitting on your desk. To fully describe that coffee at the quantum level, you need to know the position, momentum, and quantum state of every single particle in it. Every water molecule, every dissolved coffee compound, every photon bouncing off its surface. This complete description is what physicists call information. Now, here's the key insight that emerged from quantum mechanics in the 1920s. Developed primarily by physicists like Heisenberg and Schrödinger, this information evolves in a very specific way. The evolution is what mathematicians call unitary, which is a fancy way of saying it's reversible. If you know the quantum state now, you can calculate what it was in the past or will be in the future. This isn't just some abstract principle. It's baked right into the Schrödinger equation, which governs how quantum states change over time. Where psi is the quantum state, h is the Hamiltonian, the total energy, and I is the imaginary unit. The crucial point is that this equation is perfectly reversible. You can run it forward or backwards in time. When your book burns, the information isn't destroyed, it's scrambled, spread out among the ashes and the heat. But it's still there, encoded in the quantum state of all those particles. This is information conservation, and it's as fundamental to physics as conservation of energy. Black holes entered theoretical physics in 1915, the moment Albert Einstein completed his general theory of relativity at the Prussian Academy of Sciences in Berlin. Within months, a German physicist named Karl Schwarzschild, who was serving in the German army on the Russian front during World War I, found an exact solution to Einstein's equations. This solution described what we now call a black hole, though the term wouldn't be coined until 1967 by John Wheeler at a conference in New York. The defining feature of a black hole is its event horizon, a boundary in spacetime beyond which nothing, not even light, can escape. The radius of this boundary is called the Schwarzschild radius, and it's given by this formula, where g is Newton's gravitational constant, m is the mass of the black hole, and c is the speed of light. For most of the 20th century, physicists believed black holes were the ultimate information destroyers. You throw your book into a black hole, it crosses the event horizon, falls towards a singularity, and from the perspective of anyone outside, that information is simply gone. The black hole doesn't care what fell in. It only has three properties that an outside observer can measure: mass, electric charge, and angular momentum. This was encapsulated in a phrase coined by Wheeler in the 1960s. Black holes have no hair. But then, something remarkable happened. In 1974, Stephen Hawking, working at the University of Cambridge, combined quantum mechanics with general relativity in a way no one had done before. He asked, what happens to quantum fields right at the edge of a black hole's event horizon? What Hawking discovered was completely unexpected. black holes aren't completely black. They radiate. Here's how it works. In quantum field theory, even empty space isn't truly empty. Vacuum fluctuations constantly create particle-antiparticle pairs that pop into existence and immediately annihilate each other. This happens everywhere all the time, but we don't normally notice them because these virtual particles exist for such short times. But at the event horizon of a black hole, something special can occur. One particle of the pair can fall into the black hole while its partner escapes. To an outside observer, it looks like the black hole is emitting radiation. This is Hawking radiation, and Hawking calculated its temperature in his landmark 1974 paper. The temperature is minuscule, given by the following formula. For a solar mass black hole, this temperature is about 60 billionths of a degree above absolute zero, far colder than the cosmic microwave background. But for tiny black holes, it can be much higher. Now here is where the paradox emerges. This radiation carries away energy, which means the black hole slowly loses mass. Over vast stretches of time, much longer than the current age of the universe for stellar mass black holes, the black hole will completely evaporate. It will disappear entirely, leaving behind only the Hawking radiation. But here's the problem. Hawking's calculation showed that this radiation is thermal. It's completely random, characterized only by the black hole's temperature. It contains no information about what fell into the black hole. If we threw our book into the black hole eventually evaporates completely. The radiation that comes out is random thermal noise. Where did the information about the book go? According to Hawking's calculation, it's just gone, destroyed, vanished into the universe. This violates unitarity, that sacred principle of quantum mechanics that information is always conserved. When Hawking presented this result, the physics community was divided. Some physicists accepted his conclusion. Maybe information could be destroyed after all. Perhaps quantum mechanics needed to be modified. Hawking himself initially took this position. Others absolutely hated this idea. Prominent among the skeptics was Leonard Susskind. In the early 1990s, Susskind began arguing that the information must somehow be preserved. This led to what Susskind later called his battle with Hawking, a friendly but intense scientific disagreement that lasted decades. One proposed solution came from the holographic principle. The idea is radical. Perhaps the information that falls into a black hole isn't really lost inside. Instead, it might be encoded on the event horizon itself, smeared out over its surface like a hologram. If we throw our book back towards the black hole, as it approaches the event horizon, from your perspective, watching from far away, it appears to slow down, flatten out, and spread across the event horizon, taking an infinite amount of time to actually cross it. The holographic principle suggests this isn't just an optical illusion. The information really is stored on the horizon's surface. In recent years, several promising ideas have emerged, though none have solved the paradox. In 2019, Hawking himself changed his position in a paper co-authored with Malcolm Perry and Andrew Strominger from Harvard. They proposed that black holes might have soft hair, subtle quantum properties at the horizon that could store information. Another potential breakthrough came from Jeffrey Pennington at Stanford and others who calculated something called the Page curve, named after physicist Don Page, who predicted it in 1993. This curve describes how the entropy of Hawking radiation changes over time as a black hole evaporates. The new calculations showed that at late times, using quantum extremal surfaces and techniques from quantum information theory, the radiation's entropy starts decreasing. This indicates that information is indeed coming out, encoded in subtle quantum correlations between different bits of Hawking radiation. Think of it like this. At first, the radiation looks completely random, but as more and more radiation is emitted, careful correlations between early and late radiation begin to carry information. It's as if your book's pages were scattered across time, but the words could be reconstructed by analyzing how all the scattered pieces relate to each other through quantum entanglement. Where does this leave us? As of 2025, most physicists believe information is preserved, although the precise mechanism does remain mysterious. The paradox has driven enormous progress in understanding quantum gravity, holography, and the fundamental nature of spacetime itself. If you found this interesting, it helps the channel a lot if you hit that like button. It tells YouTube to show it to more people who might enjoy this content. And if you want to see more videos breaking down the math and history behind the universe's wildest phenomena, consider subscribing. Thanks for watching, and I'll see you in the next one.